Quantum teleportation is real. Not science fiction, not a thought experiment, an actual phenomenon that physicists have demonstrated in labs. And this month, researchers in Japan just cracked a 25-year-old puzzle that brings it significantly closer to practical use. Here is the strange part. For quantum teleportation and quantum computing to actually work at scale, scientists need to be able to read quantum states in a single instant. Not after thousands of measurements, instantly. And for one critical type of quantum state, they had never been able to do that. Until now. Let's back up. Quantum entanglement describes a situation where particles, usually photons, become so deeply linked that you cannot describe them one by one. The system has to be treated as a whole. Einstein famously hated this idea, calling it spooky action at a distance. But today, entanglement is not a curiosity. It is the foundation of quantum computing, quantum communication, and quantum teleportation. There are different types of entangled states. The most famous is the GHZ state, named after Greenberger, Horn, and Zeilinger. Scientists figured out how to identify GHZ states with a single measurement over 25 years ago. But there is another important type called the W state, and it had resisted that same kind of instant identification for over 2 decades. What makes W states special? They are unusually resilient. If you lose one particle in a GHZ system, the entanglement collapses. In a W state, lose one particle, and the remaining particles stay entangled. That makes W states particularly attractive for real-world quantum communication networks, where signal loss is unavoidable. It is the more practical option, and it was the one nobody could read quickly. The problem was that standard quantum tomography, the usual tool for figuring out what state you have, requires the number of measurements to grow explosively as you add more photons. For large systems, it becomes completely impractical. Scientists needed a way to identify a W state in one shot, and nobody had proposed a way to do it. Not in theory, not in practice. Researchers from Kyoto University and Hiroshima University, publishing in Science Advances, changed that. Their key insight came from a property unique to W states called cyclic shift symmetry. Using that structural feature, the team designed a photonic quantum circuit that performs a quantum Fourier transformation tailored specifically to W states. In practical terms, they built a device that takes in carefully prepared photons and, based on how those photons exit the system, identifies which W state is present. No massive data collection, no repeated measurements, one shot. They demonstrated this with 3 photons using stable optical quantum circuits that ran for extended periods without needing active calibration. That stability matters enormously. Real quantum technology cannot depend on constantly adjusted laboratory setups. Corresponding author Shigeki Takeuchi put it plainly. More than 25 years after the initial proposal concerning the entangled measurement for GHZ states, we have finally obtained the entangled measurement for the W state as well. The applications extend across the field. Quantum teleportation, which transfers quantum information without moving matter, gets a significant practical upgrade. Quantum communication networks, where W states could become the standard for maintaining entanglement across lossy fiber links, now have a reliable detection method. And measurement-based quantum computing, which uses entangled states as a computational resource, now has a tool it never had before. This is not happening in isolation. In April 2026, researchers demonstrated photon teleportation across 270 meters of existing urban fiber optic cables with a fidelity of 82%, well above the classical limit. And earlier this year, an integrated photonic chip was reported that generates, manipulates, and measures complex entangled states, all on a single device. The pieces of a real quantum internet are coming together, and the ability to instantly identify complex entangled states is one of the most important of those pieces. The Kyoto team is already planning to extend the method to larger, more general multi-photon systems and to build on-chip photonic circuits that perform these measurements at a compact, scalable scale. A quarter century after the last major milestone in quantum state identification, the W state has finally been solved. Quantum networks are getting closer. Quantum computing is getting closer. And what once seemed like the most exotic corners of physics is quietly becoming engineering. Like, subscribe and hit the notification bell to stay updated on the latest in cutting-edge technology.